I thought you were going to say he's also very fit, but you then said to do the job, so I was a bit disappointed. When we're at school, we're often asked to make a choice, Shakespeare or the second law of thermodynamics, Rubens or relativity, Debussy or DNA, art or science. And when I was at school, I was deeply frustrated by this sort of desire for the education system to put me into this art or science box. When I was about 12 or 13, I sort of started to fall in love with the world of mathematics. I enjoyed the way this language kind of explained the way the world worked, helped us to make predictions about where we were going next. Its incredible logical side. I also fell in love with science. But it was about the same time that I started learning the trumpet, started to play a lot of music, really enjoyed the musical world, I did a lot of theatre and things. And so I found it deeply frustrating that I was somehow asked to make a choice about my career path, my educational path, about choosing to be a scientist or to be an artist. And I suppose I've called this the two cultures, a false dichotomy. The two cultures, of course, comes from this lecture that C.P. Snow gave about the problem of the sort of a divide between these two camps. Now, I actually turned out to be better at doing maths than playing the trumpet, and so I chose the scientific route. But ever since I've been doing my science, becoming a mathematician, proving theorems, I've always kept a love of the arts and music. I listen to a lot of music when I'm doing my mathematics. And I've done a lot of collaborations with artists over the time. I've collaborated with Complicité on their theatre works, with some composers. And so I've always been interested in, really, is it really true that it's sort of two different camps? And as I've explored these two areas, I realise actually we are quite often interested in exactly the same things, about structures that interest us. And intriguingly, the structures that artists often are drawn to are often the same sort of structures that I find interesting from a mathematical perspective. So in this talk, I haven't got enough time to look at the whole of the arts and the sciences, so I've just chosen a particular example to illustrate this kind of dialogue between the world of art and science. And I suppose the dialogue between mathematics and music has always been one that people have talked about. So I've taken a particular composer, one of my favourite composers, who is Olivier Messiaen. Olivier Messiaen was a French composer during the 20th century, and a lot of his music deliberately seeks out mathematical structures. He loved mathematics in order to create certain effects. One of my favourite pieces of Messiaen is a quartet he wrote called the Quartet for the End of Time. This quartet he wrote whilst he was a prisoner of war in Germany during the Second World War. In the prisoner of war camp, there was an upright piano. He played piano, and he discovered there was a clarinetist, a violinist, and a cellist also in the camp. And so he wrote this quartet to express the kind of terrible times that are happening, and wanted to create a sense of timelessness in this first movement, the Liturgy de Christa. And in order to create a sense of unease and never-ending time, what he did was to use a bit of mathematics. He knew about prime numbers. Prime numbers are these indivisible numbers like 7 and 17, things that can't be divided by anything but themselves and 1. And he used these primes to create this sense of unending time. So in the first movement, the clarinet and the violin exchange bird themes. He was very obsessed by bird themes. But it's in the piano where you see these use of these prime numbers to create this sense of unease. So in the piano piece, and this is the score for the piano piece, the piano plays a 17-note rhythm sequence. And after 17 notes, it repeats the same rhythm again and again throughout the piece. So let's see where, pressing that line. There we go, that's the red line there. So the rhythm starts crotchet, 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 then does a nice syncopated rhythm, and then repeats after 17 notes, crotchet, crotchet, crotchet again. The harmonic sequence, however, is doing something else. It has a 29-note harmonic sequence, and after 29 notes, it then starts repeating itself. But at that point, the rhythm is only about 2/3 of the way through its pattern, and when the rhythm finishes again, the harmony is somewhere else. And so the two things, by using the primes 17 and 29, Messiaen very carefully keeps the two things out of sync. The piano just repeats this, the harmonic sequence, 29 notes again and again, the rhythm, 17 notes again and again. But because they never interact in the same way each time they're repeated, you get this sense of unease and eventual timelessness because you have to hear the thing 17 times 29 times before you hear it actually come full circle again, and the piece is finished by that point. So let's hear these primes 17 and 29 in action in the piano piece. So the rhythm is finished, it starts again. The harmony is still working its way through its 29 sequence. Harmony is finished and starts again, but the rhythm is somewhere completely different. Now, of course, Messiaen doesn't expect you to hear these primes 17 and 29 because it's such a long sequence of time, but he does want you to feel the effect of these structural numbers not interacting, keeping out of sync. And interestingly, Messiaen is picking up on something that nature has been using for a long while. There's an interesting insect in North America, a cicada, which uses the same principle of these primes to keep it out of sync for its evolutionary survival. This species of cicada has extraordinary life cycle. It hides underground doing absolutely nothing for 17 years. Then after 17 years, the cicadas all emerge en masse from the ground and they party away. This is the sound of one cicada. You have to multiply this by millions of these things in the forest. The sound of the forest is so loud that most residents move out during this 17th year. They party away, they eat the leaves, they mate, they lay eggs, and then after 6 weeks of partying, they all die, fall to the floor, and the forest goes quiet again for another 17 years before the next brood appears. I mean, it's an absolutely extraordinary life cycle. How the cicada is counting to 17, we don't know, because there's nothing in the natural cycle which has a 17-year cycle. Sunspots have 11 years, but we're not even too sure how they managed to do this. But why are they choosing 17? Prime number is the prime number Messiaen used in his work. Is it just a coincidence? Well, we think not. There's another species of cicada in North America which appears every 13 years. And over in North America, you can find different species. They either choose 13 or 17. Never 12, 14, 15, 16, or 18. Just these primes, 13 and 17. So we think there's something about these primes which is helping these cicadas. And we're not sure what it is, but we think it's the same trick as the Messiaen. We think that this prime number life cycle keeps it out of sync of maybe a predator. So, for example, if there's a predator that appears periodically in the forest, say every 6 years, then a cicada that appears every 9 years is going to get in sync with the predator very quickly, because every 18th year the cicadas and the predator are in the forest, so it gets wiped out. But a cicada that has a 7-year life cycle, well, because the 7 is a prime number, it can keep out of sync much better of this predator, and so the cicadas and the predator only meet for the first time in year 42. So those cicadas which have a prime number life cycle seem to survive much better because they can keep out of sync. In the forest in North America, there seems to be a real competition between who knows their primes better than the others. The cicadas got up to 17, predators wiped out. So a message there, if you know your maths, you survive in this world. But it's interesting because Messiaen is picking up on something which is already there in the natural world. And I think that's often what we're doing. We're responding to structures in the natural world around us, either from an artistic point of view or from a mathematical point of view. But intriguingly, sometimes artists are drawn to, in that piece, the Quartet for the End of Time, Messiaen knew what he was doing. He knew his prime numbers. He knew how to create this effect. But sometimes artists are drawn purely for aesthetic reasons to structures which have huge mathematical significance. Messiaen was actually a follower of Arnold Schoenberg's method of writing music. In Schoenberg, at the beginning of the 20th century, they threw away tonal music and replaced it with atonal music, where each note of the chromatic scale was given equal value. But you need some structure. If you're going to throw tonal music away, you need to put in new structure. That new structure was very mathematical. So Schoenberg would do a permutation of these 12 notes to create these 12-tone rows. So he would arrange the 12 notes of the chromatic scale in some interesting way. And then he would do mathematical operations on these. He would do reflections, translations, rotations to create a palette of 48 tone rows, which he would then use to do his composition. Messiaen fell in love with this way of creating a palette of musical themes from which to compose. And interestingly, in a piece that he wrote for solo piano, so this called the Il de Faux 2, in this piece he chooses two 12-tone rows, so two permutations of 12 notes, which he felt had some interesting relation to each other. So when you played them on the piano, it sort of had some sort of strange connections with each other. Now, from a mathematical point of view, if you view these two 12-tone rows as permutations of 12 things, then it actually generates a symmetrical object in my world. The world that I research is the world of symmetry. There's an incredibly exciting mathematical object which we call M12. It's a symmetrical object I can't show you because it lives in very high dimensional space. But the discovery of this at the end of the 19th century gave rise to the discovery of kind of exceptional symmetrical objects out there in the mathematical world. Now, interestingly, Messiaen's two 12-tone rows, when viewed from a mathematical perspective, and you generate the symmetrical object which are associated to these two permutations, creates this object M12 that mathematicians have been drawn to purely for mathematical reasons. Messiaen knew nothing about this object. It's only been very recently observed that Messiaen's piece, Il de Faux 2, actually captures this symmetrical object. So although I can't show you this high-dimensional object, I can actually play it for you. So here's M12. That's the beginning anyway, but I prefer the mathematical version. I think it's slightly more beautiful. But, and that's interesting because mathematicians often talk about beauty in their subject and talk about aesthetics. I mean, it's kind of maybe more obvious that artists are plundering the scientific toolbox to find interesting structures. But I think mathematicians often talk about their subject and talk about the beauty of their proofs. And one of the books that really excited me when I was a 12 or 13-year-old and got me into doing mathematics was one of the books I've recommended outside. Unfortunately, it's out of print at the moment. It's going into a new print. It's a book called A Mathematician's Apology by G.H. Hardy, who was a Cambridge mathematician in the 20s and 30s. And he wrote, "A mathematician, like a painter or a poet, is a maker of patterns. I'm only interested in mathematics as a creative art." And actually, Graham Greene wrote about this book that this is the best example of being a creative artist after Henry James's diaries. And so this book talks a lot about the creativity of maths. And I think most mathematicians, if you ask them why they do their subject, will not say, I do it for utilitarian reasons. I do it because I want to solve the problems of the world. They'll say they do it for similar reasons to the artist creates their work. They want to create new structures. They're interested in it for its own right. And certainly the mathematics that I do and the mathematics I appreciate, I choose the mathematics that I do because it tells an interesting story. And for example, one of my favorite mathematical theorems is a theorem of Pierre de Fermat. He proved many beautiful theorems, and one, he said, if a prime is divisible, if you take a prime number and you divide it by 4 and you get remainder 1, so something like 41, then you'll always be able to write that prime number as two square numbers added together. So 41 we can write as 4 squared plus 5 squared. So however large your prime number is, half of them when you divide by 4 have remainder 1, you'll always be able to write them as square numbers. Now, I've never seen this being used in any practical way in the modern world or before. However, this is a beautiful theorem, and actually it's not the result that's so important, but the journey that Fermat takes you on in the proof. Because you start with the prime numbers which leave remainder 1 on division by 4, and then as the piece goes on, you suddenly see the arguments mutating this prime until there's some magical moment when it starts to become square numbers. And it's almost like listening to a piece of music. And when I read this proof, and the way I read proofs is very similar to the way I listen to music, you can almost feel themes being established, somewhere where you're happy, and then they start to interweave and take you on a journey to somewhere new. And that's what mathematicians are after. They're after telling stories that have exciting journeys, and it's not very often just the final result. So for example, I don't expect you to understand this, but this is my greatest discovery in the world of mathematics, which was a new symmetrical object, which again lives in just very high dimensional space. But I could get a computer to churn out endless new symmetrical objects, new mathematical theorems. But the role of the mathematician is like the artist. I chose this particular symmetrical object to stand up in my seminars, to write journal articles about, to write books about, because it tells an extraordinary story which connects the world of symmetry with a completely different area of mathematics called elliptic curves, some area of number theory that we still don't really understand. And so mathematics is a lot about choices, and those choices often motivated by the same aesthetic decisions that an artist has and the same sort of structures that the artist is drawn to. I'm going to end with this quote here. Well, I've got another quote after as well, but this quote here, I want you to think whether you think this is a quote written by a mathematician or an artist. To create consists precisely in not making useless combinations. Invention is discernment, choice. The sterile combinations do not even present themselves to the mind of the inventor. So how many people think that that's an artist talking about their subject? Put your hands up if you think it's an artist. Quite a few votes for the artist. How many people think a scientist? A bit more, maybe the word inventor. Artists don't tend to call themselves inventors. How many people are not sure? Could be either. After this talk, you should be perhaps all putting your hands up now. But, well, in fact, the word inventor is intriguing because actually Stravinsky used to call himself an inventor. So he felt that he was inventing the music that he developed. But it is, in fact, a mathematician. It's a very famous mathematician, Henri Poincaré, the discoverer of chaos theory. And it certainly expresses what I believe about the mathematical world. Although the logic of mathematics forces things to be either true or false, there are so many true statements out there. After all, half the statements are true in mathematics. It's about making choices about which ones are you going to bother talking about and exciting people about in the seminars and papers that you write. So it's just in the same way as there are infinitely many pieces of music, it's about choosing the combinations of notes that say something to the soul. And in fact, one of the other books that I chose, which is outside, which is a very formative book that I read as a student, is a book called The Glass Bead Game by Hermann Hesse. And the Glass Bead Game, for me, I don't know, has anybody read the Glass Bead Game here? A few readers of the Glass. You must read this book. This captures, for me, what we should be doing in our education system and beyond, which is breaking down the barriers between all of these subjects. Stop talking about subjects being maths or history or music or culture or art. They're all part of the same subject. And in this book, they play this wonderful thing called the Glass Bead Game, which sort of tries to combine all of the subjects into one fusion. And I think that's what I've been doing all my life, is really trying to play this Glass Bead Game. The symbols and formulas of the Glass Bead Game combine structurally, musically, and philosophically within the framework of a universal language, were nourishing by all the sciences and arts, and strove in play to achieve perfection, pure being, the fullness of reality. And that's what I think we should all be doing. Thank you.